Hello everyone. In this video we're going to be taking a look at the instantaneous power equation. We're going to do a derivation of this equation and then a couple examples where we get to use this equation in different contexts. So to do this derivation we're going to start with the following equations. Our main equation will be power is the change in energy over time, and then we're going to use work is equal to the force times the distance times cosine theta, and work is also equal to the change in energy. The first thing we'll do to start this derivation is we're going to show that power is actually just equal to the work done by an object or by something on an object over the change in time. We can then use the equation for work as FD cosine theta, and we can substitute that in for the work term in our power equation. So what we've essentially done is we've changed power as change in energy over change in time to power is equal to the force times the distance times cosine theta over the change in time. The next step we're going to take with this derivation is to look and see that we have a distance over a change in time in this equation. And distance over a change in time is from our kinematics unit, and distance over a change in time is equal to the object's velocity. So using this fact, we can take out distance over time and we can replace it with the velocity term. So we get that the power is equal to the force multiplied by the velocity multiplied by cosine theta. So if we then attach the instantaneous as a subscript on the velocity, we get the instantaneous power equation. The instantaneous power generated by a moving object is the force on that object multiplied by the instantaneous velocity multiplied by cosine theta. So as always, we're going to practice using this equation with an example problem. And this example problem is twofold. We want to practice using this equation, but we also want to show the difference between average power and instantaneous power. So we're going to calculate both of these two things in this problem. So we know the object's mass. We know that the force pulling the object across the horizontal surface is a constant force of 10 newtons. We know that it's applied over a distance of 5 meters and it's starting from rest. So if we want to calculate the average power, all we need to do is calculate the average work done by that force by doing force times distance, and that's going to be the change in energy of the block. If we divide that by the time, then that's going to give us the average power generated by that force. And that average power ends up equaling 34.46 watts of power. And so now somewhere along the motion of this block, it ends up reaching some speed of 4 meters per second at some point in time. And if we want to calculate the power generated by this force at that particular point in time, then we need to use the instantaneous power equation. So we know the instantaneous velocity is 4 meters per second, and all we need to do is do F times V times cosine theta. That force is still 10 newtons, but cosine theta is going to be 1 because the force is applied in the same direction as the velocity, meaning the angle between them is 0 and cosine of 0 is 1. So to find the instantaneous power generated at this point in time, we're just going to do 10 times 4, and we're going to get 40 watts. So we see is the average power exerted over this distance is not equal to the instantaneous power at this particular point in time, and it won't be equal to the instantaneous power at several points in time. So this is very similar to how the average velocity and the instantaneous velocity don't always line up during accelerated motion. But if we also remember that the instantaneous and average velocity do equal each other if the object is moving at a constant velocity, we get the same type of rule here for instantaneous and average power. So if you take a look at an example where an object is moving at a constant velocity due to a constant force being applied to maybe resist or counteract a constant force of friction to maintain a constant speed of 0.5 meters per second over some distance. So just like we did before, to calculate the average power generated by the force pushing the object to keep it moving at a constant velocity, we're going to do the work done by that force over that distance divided by the time, because once again the work is the change in energy. So we're going to do 5 newtons multiplied by 0.8 meters, and then we're going to divide that by the time it takes to move that distance. Now to figure out that time, we do need to do a little bit of kinematics. Since we know that the object is traveling at 0.5 meters per second and it travels 0.8 meters, to find the time we just need to do 0.8 divided by 0.5. So using the force value of 5 newtons, multiplying by the distance value of 0.8 meters, and then dividing by that time we calculated of 1.6 seconds, we get that the average power output of this force is 2.5 watts. Now if we want to compare the average power output to the instantaneous, we need to calculate the instantaneous. So we know that the object is moving the same speed over the entire duration of time. So to find the instantaneous power, we just need to do the force of 5 newtons and then multiply that by the velocity of 0.5 meters per second, which is going to give us 2.5 watts, just like we got in the average power equation. So this just reiterates that while an object is moving at constant velocity, the average power and the instantaneous power generated by some force are going to be equal to each other. And that's it on this video for introducing the instantaneous power equation with a couple examples. Thanks for tuning in, and I'll see you next time.